So, Jason, neither of us is crazy about the word PQC.
Post-quantum cryptography. What does that even mean?
What? Yes.
Because, I mean, we had Dustin Moody on.
Yeah.
We're doing pre-quantum resilient computing cryptography, right?
Yeah.
The words are silly.
It's a weird word. And you and I, early on when we were talking about this before the industry had settled on a term, we kind of liked quantum resistant. Yeah. I still like quantum resistant cryptography better, but it lost that war. But I think you've got an idea for taking PQC back.
Yeah, let's take it back.
Let's take the word back.
Because I'll tell you where it applies more.
Mm-hmm.
Take that C, take away cryptography.
Okay. Yeah, who needs it? Get rid of cryptography. Who needs it?
Quantum resilient, quantum resistant, far better terms. That's what I'm always going to advocate for.
Sure.
And you're going to hear me say it. You're going to hear Tim say it.
Yep.
Take the C and change it into what's the world going to look like after we have a cryptographically relevant quantum computer? It's going to change civilization.
Okay.
Post-quantum civilization, Tim.
Post-quantum civilization, PQC. I love it.
Yeah.
Which, by the way, is going to be full of post-quantum companies, PQCs. So what does post-quantum civilization look like?
Tim, here's a really deep but impactful thing that happened in the last few years.
Okay.
Very young researcher came up with this idea that, hey, there's a whole lot of things in terms of modeling that we thought we would require a quantum computer to be able to do at scale that we can't do with today's digital computers.
Okay.
And it ends up turning out a lot of those things are in medicine or material science. Not all of it, but there's a whole lot of science going on right now in what's called de-quantizing a problem.
So I'm guessing from the word what that means, but just define that for us.
The simplest way I can say it is this. What people didn't anticipate when quantum computers, very basic, small-scale quantum computing first came out, was to realize that, oh, wow, it really takes a lot to be able to feed a quantum computer what's necessary in order to do the experiment. So would it take less time to use a traditional computer? That's the basic question being asked by de-quantizing.
All right.
It turns out there are a whole lot of modeling problems that can be solved by merely having a better way to feed data so that it is inherently structured for a traditional computer to do the modeling.
So is this something we could have done at any time?
Yes.
If we had had the insight?
Yes.
And we just didn't have the insight?
The insight is literally within the past couple years.
And was that insight driven by the fact that quantum computers forced us to think differently about these questions?
Yes.
Okay. So you don't need a quantum computer at all for certain problems. You just need to understand, I'm going to grossly oversimplify, understand how to ask the question. And we needed the framework of quantum computing to help us understand how to ask that question correctly.
Scientific community, the modeling community, everything from climate modelers to material science modelers to you name it.
So this is fantastic news because one of the things we've been doing is we've been waiting for quantum computers to get to the point. Now, in the case of a QRQC, we've been worried about them getting to the point. But in case of the good benefits, the one we want, we've been waiting for them to get to the point where we can start reaping those benefits. But it sounds to me like you're saying, at least in some cases, yeah, we can start reaping them now, and we are.
There is a land rush to de-quantizing as many things as possible so that we can start applying traditional compute against it.
Which we have, for our purposes, an infinite quantity of.
More than we've ever had. I mean, there's so much compute available right now.
Yeah.
It's unbelievable.
Yeah.
A lot of it's being eaten up by AI.
Right.
But on the other hand, we now know how to build compute traditional compute at scales we've never thought of before.
Absolutely. Right.
So, to the point where we need nuclear plants to run all the new compute we have.
We're
It's
running
it's
out of
crazy.
electricity.
It's
Absolutely.
crazy.
Yeah.
However, it's worth saying that there are problems that cannot be inherently solved just from a better data structure or modeling.
Okay.
In other words, non-dequantizable problems, of which cryptography.
Is Shor's algorithm one of those?
Shor's algorithm is one of them.
Yeah. I was imagining.
I would put it at the top of the list.
Yeah.
And that's why I mentioned a cryptographically relevant quantum computer, even in the sense of material science or finding new medicines, protein folding, you name it. It's because all of those things, once you get up to something that's could run Shor's algorithm,
Yeah.
surely you've got enough stable qubits to do material science and et cetera, right?
Yeah.
Financial studies. It's all these things that can benefit. But it's an exciting world, Tim. And it came out of quantum computers teaching us how to do classical computing better.
Yeah. That's great. Fascinating. I love it. Post-quantum civilization.
Yeah, post-quantum civilization, just to put a little finer point on it, is this. Tim, when we have cryptographically relevant quantum computers,
Yeah.
Of course, you and I are already busy people dealing with that inevitable world. I mean, but I would say that if you are at all in like, okay, I am building the next generation aircraft material that to be, an order of magnitude lighter, stronger than it is today. If I'm folding proteins and I can solve a major problem in human DNA, these are all life-changing.
These are very important. Absolutely.
Civilization pivoting moments.
Yes.
That are going to happen when we have quantum computing with a sufficient number of stable qubits.
Yeah. Right.
It will change civilization, post-quantum civilization.
Post-quantum civilization. I love it.
Thank you,
Jay.
Jim.